Okay, hi everyone, I'm Silviu, and today I'm going to talk to you about some cool tools for deploying, let's say, a little bit more optimized computer vision and AI algorithms from cloud to edge. So, first part of the talk will be about these tools and how to use them and deploy one and use them in our workflow. And the second part will be about the real world use case to see how exactly you can put this into practice and create a product with it. All right, so just to get to know you better, how many in the room are actually developing with AI right now? So there's a few in the room. And how many of you are doing computer vision specifically? Okay. And from this subset, how many of you have worked with OpenVINO? All right, so we have some OpenVINOers in the room. But the rest of you will become OpenVINOers in the next 30 minutes, I guess. Yeah, so the first part is CV and AI tools for deep learning with OpenVINO toolkit. Now, OpenVINO comes from Open Visual Inferencing and Neural Network Optimization, right? It's a set of tools that allow you to create and deploy faster models, basically. Now, it offers you tools for deploying at the edge, deploying on PCs, or deploying on edge devices, or cloud. It depends on your use case. Now, from my perspective, it's all about performance, first and foremost, then robustness, so having some core that you can rely on and it always works as you expect, and of course flexibility. So maybe today I want to run my models in a cloud API somewhere, but maybe those same models could be applied somewhere on-premise without any connection to the cloud. So then I want to run them on an edge device, and if possible, on a low-power, cheap edge device. So then you have some trade-offs to do, but with OpenVINO, you also have a lot of flexibility because you can basically use the same toolset to run in all of these scenarios. So yeah, here's a little bit of description from Intel, because they're actually providing distribution for OpenVINO. So OpenVINO is an open source project, but they also provide already built binaries to use it and run it on your machines. Now, as I said, it's a multi-platform thing, so there's a lot of hardware support. So there's a common API for running inference on your models. So once you've built them, you can run them on CPUs, GPUs, VPUs, which you'll learn a little bit about them later, and FPGAs. I'm sure everyone's common with those. And there's a huge bunch of OS support. So basically, there's a trifecta. So you have the Linux, you have Ubuntu, you have CentOS, you have Yocto. Who in the room uses either of these to develop? So quite a few people are using this. Who uses Raspbian? Cool. So some people develop IoT mostly, right? So yeah, and also Docker. So of course you can run a Docker inside Linux and have everything there. Next, Windows. Who in the room develops on Windows? I'm expecting more hands. No? Oh, so not that many developers then. What do you develop on? Is it Mac? Who develops on Mac? Okay, so a few hands here. So basically, yeah, you have Linux, you have Windows, you have Mac, so anything PC or cloud, you can deploy in. Now, let's talk about development tools, right? This is actually the... No, for Mac it's more limited. You know, Mac. But it works, so still a big deal. So development tools, right? This is the big part. So this is not super readable. Yeah, so here's actually the full distribution that is provided by Intel. So I'm going to read it to you because I'm not sure you can see it. So first, there's an inference engine, which is a big part. That part takes trained models or intermediate representation models and allows you to run them very fast using C++. Then you have a component called Model Optimizer, which takes any model you've trained in your specific deep learning framework and converts it to a model type that can be consumed by the inference engine. And then there's a deep learning workbench, which allows you to do, let's say, on-the-fly operations on your models. Then you have OpenCV. Who in the room used OpenCV? This should be popular. Yeah, OpenCV is really good. You have OpenVX, which is quite similar to OpenCV. It still helps with image processing. Then you have an Open Model Zoo. That's a concept that is familiar with many, let's say, deep learning environments. And Media SDK. Okay, in this talk, we're going to focus on these three. So there's the model optimizer, which is, I would say, the first step in our workflow. All right. So model optimizer is basically a command line or Python conversion tool that allows you to translate your model from training or from development and to get it to your deployment environment in a really nice package. So here are the supported frameworks. This is another question for you guys. Who uses TensorFlow in the room? Cafe? Not so many cafes. MXNet? I'm guessing no one. And you have ONNX, which is a unified model which you can basically convert TensorFlow or Caffe or whatnot into it. Now, let's imagine that you have trained a neural network. How many in the room have trained a neural network or used it? Okay, cool. So a lot of trainers. So let's assume you have trained your neural network. Now you have two classes. You have cats and dogs. And it's working pretty well. You're super happy, 99%, everything is awesome, right? So you have this, you have it in Caffe, MXNet, TensorFlow, whatever. And the next step would be to run the model optimizer. And the model optimizer will convert your model into two files, an XML and a binary file, which contain all the data previously trained in your model. But this data type can be easily consumed next by the inference engine. So the inference engine is really cool, as you can hook it inside your application. So then you can just call it inside your app, C++ app or Python. And you can also instruct it to run on CPU, to run on GPU, to run on VPU or FPGA. So basically, you can run inference on whichever device you prefer, or all of them. So it's really a really interesting way to deploy, and it's also very performance-oriented, if you will. Right. So yeah, let's do a walkthrough, right? Because I told you you can do it, but let's see how you can do it actually, right? So this is an example with TensorFlow. So I went with TensorFlow because it's probably the most popular deep learning framework, and I'm sure everyone in the room has at least taken a look over it. And yeah, the idea is this assumes that OpenVINO is installed or built on your system. Basically, you just need to navigate to model optimizer install prerequisites and just run the script. If you want to do it in a virtual env, so you don't install a lot of stuff in your main, then yeah, you can do the other optional white steps or whatnot. Right, so now you have a TensorFlow model and you want to freeze it. Maybe, I don't know, you may want to freeze it. So here's the code to freeze the model. Then you get the PB file at the end. And with the PB file, it gets super easy. You just run this thing. So you have a Python script. It's model optimizer underscore TensorFlow. And you just set the input, and it will output the IR or the bin file and the XML that you required for later to serve the inference engine. Nice. But let's say you don't have a frozen model, right? And you just want to convert a specific checkpoint in your model. So in that case, you do this. You use some different commands a little bit. You just state the checkpoint. And it doesn't matter if you have a PB format or a text format. It'll still work. And you're going to get your converted model this way as well. What if you use a metagraph? Well, you see different inputs, but the output is the same. And again, you just use the same script to convert them. Oh, and last but not least, if you have a non-frozen safe model, you use this command. Because in some cases, you might have some more complex structure or folder structure to your model, and then this is what you would use. Okay, now let's take a step forward and go with something more complex, like translating a YOLO model. you guys might have heard about YOLO before, right? I have a short video. I'm not sure if this was the same that got played before. Okay, let's see.
But she only cares when she's so inclined. And I fret so much about her loving. I wish she'd let me be, but her destiny's got us so intertwined. Back in 2011, I decided to not let this play with my mind. But when them boys from out of town, they come back around, I feel like committing a crime. Yeah, I get jealous, but I'm too cool to admit it. When the fellas talk to my girl, I ain't with it. I get jealous, but I'm too cool to admit it. When the fellas talk to my girl, I ain't with it. I get jealous, but I'm too cool to admit it. When the fellas talk.
Cool. So I think you got a gist of what YOLO can do, and it's really impressive because with YOLO you get both performance and really good quality and accuracy in detection, and that makes it a perfect candidate to run your real-time inference using this kind of network, right? So here's how you can convert YOLO to work for your application, right? Let's say you wanna first get the repo. So there's a TensorFlow Git, which is basically just the YOLO detector. You cannot do any further training. So you would use pre-trained data from the YOLO v3 guys. So you get this repo, and then you would download the weights from the YOLO website, weights and class names, which are Coco names and weights file. And then you would run Python convert weights, and this will basically convert everything to work right with the model optimizer. So yeah, next you just run the model optimizer, and voila, you have YOLO, and you can run it anywhere. You can run it on really small devices. You can run it in the cloud, and you can perfectly integrate it in your own app. So let's talk next about the inference engine, right? Because we said model optimizer is good for getting the IR model, but now that we have the IR model and we have some really cool IR models, let's do some inference, right? How many of you do C++ in the room? Okay, quite a few, cool. So the preferred language to integrate inference engine is C++. There's also a Python wrapper, but mostly, and I think most of the, or all the functionality works in C++. So with inference engine, you have a library that allows you to load your IR models and then provides you an API to run those models on different hardware, get the outputs, and do cool stuff with them. So you have 4 main classes. You have one for reading the network, one for manipulating network information, you have one for creating an inference engine core object, and you have one to pass inputs and get outputs, right? It's super straightforward. And yeah, and you have some plugins, as I mentioned before. The plugins are those components that contain everything is required for a specific network or model to be run on each of these types of hardware. So it's seamless for you. These are already there. It just works. Right, so here's a bunch of device types. Unfortunately, yeah, it's CPU, GPU, FPGA, Myriad, GNA, hetero, and multi. Right, for CPUs, you have Xeon, you have I-Core, you have some Pentiums, or latest gen. Mostly processors which have at least AVX2 instruction sets. Those are the best because they can do a lot of single input, multiple output operations. So then it works really, really well. Cool. So here's the workflow for the inference engine, right? You load the plugin, you read the IR model, you configure what needs to be configured, you load the model, you create an inference request object, and then you have an inference loop, right? You prepare the input, you inference, and then you get the output. So everything pretty straightforward. Let's see how it looks in C++. So yeah, you just initialize everything, you read the network, and then you have a network object and an inference request object, and next, you iterate through your inputs, you read them, you put them in a variable, and then you run inference, and then you get the outputs. It's pretty seamless process. Okay, next, deployment manager. Let's say you've built your app, you've trained your network, you converted, everything is running perfectly on your system, but you would like really good way or a straightforward way to deploy this on any type of device, right? So deployment manager makes this super easy for you, right? It creates a package that will assemble everything it needs, the IR models, the application, everything that is basically required to run the model in a really nice zip. You just run a command, this gets done automatically. And let's say you're deploying on a Linux edge device or on a Raspberry Pi or something like that, something really small. You just unpack the zip or tar.gz, and then just go to the install dependencies folder, and you just ask the script to install everything for you. And if you have an internet connection, of course, it'll work. And then you just add the variables to source, and that's it. It'll just work, which is quite amazing. But sometimes you might be, more secretive. You would like other people not to have access to your model, right? You've trained it, you've worked a lot on it, and you don't want to be hacked, right? So one thing you can do, especially when going on smaller devices, like you could use the Docker for some cases, but in this case, if you're going to deploy on the edge, you can use this encryption technique, which is pretty easy to do. So you just do the following. So you have your deep learning model, use the optimizer, then you encrypt the intermediate representation of the model, and then you copy that to your deployment location. And at runtime, this encrypted network will be loaded, will be decrypted in memory, and then you're able to run your inference on the decrypted model in memory, right? Okay, so if the hacker hacks the memory, then okay, it's that can happen as well, but I think it's pretty far-fetched. There's ways to do it, but it's not super easy. Okay, cool. So next I'm going to talk to you about neural compute stick. So I said before that you have CPU, you have GPU, you have VPU. So here's the VPU. The neural compute stick is basically a high-performance, low-power vision processing unit. So this little fellow looks like this. It's basically the size of a pen drive, and it consumes about 1.5 watts to run inference. So for edge models, it's extremely useful. It's comparable in speed with NVIDIA's offering in this case, but I think it's much cheaper than that. And the idea is that with OpenVINO, you can build and deploy directly on this thing. So just to show you what you can do with it, there's also, this is how it looks. There's also a quick video running on Raspberry Pi with a Movidius or a neural compute stick, and while it's not as fast or as real-time as a CPU or GPU, this can run on maybe 7 watts of power. So you can put it in a camera, or you can put it anywhere, and it can do this in real time, or pseudo-real time. There's a mail. So that's what you can do right now at the edge, and that's pretty amazing from my point of view, at least. Next, Open Model Zoo. This is really, I think, one of the coolest parts of OpenVINO, because you have a lot of things that can get you kickstarted in your projects. So you have a lot of pre-trained models and public models that you can use and start to work with directly. You don't need to, let's say, have a huge amount of experience in TensorFlow or Caffe or whatnot to get started and test the waters and start to develop something and then go on from there. So here's a bunch of pre-trained deep learning models that you already have available with the package. So here's one for object detection. So let's say you want to do like self-driving or like assistive system for cars to detect, to make a sound when there's people crossing the street in front of you. You can do this in your car, hack an edge device and have it running. Here's another one for object re-identification. So basically it learns people's faces, and then it can identify them individually according to their own mesh, let's say. Here's one for segmentation. This is, again, useful for maybe a self-driving car scenario. Similarly here's one that segments objects that are recognized. So you have truck, you have car, you have bicycle, you have person, even bag. I'm sorry, it's not visible, but yeah, I'm going to read it to you. Here's another one for pose estimation, which is really interesting. So you can do real-time pose estimation using OpenVINO, and it's quite cool. You have like unlimited projects that you could build on top of this, right? Like think about fitness stuff and whatnot. This could be really useful to kickstart your work in that area. You also have text recognition. This is real time, so again, it can be quite handy to have your own device that doesn't need to connect anywhere that can do text recognition and whatnot. You also have action recognition. So in this case, it says that the guy is drinking and eating with a 99% accuracy. So that's also kind of handy. Here's a bunch of public models. But yeah, I'm just going to skip this page because it's not readable. So yeah, you should maybe take a photo of this slide. So you have the OpenVINO sources on the first link. Then you have the Open Model Zoo at the second link, which is very very useful and very comprehensive. So you'll find more models than you can tackle this year, probably. And the final link is the Intel OpenVINO distribution package. So you just go there. If you don't want to build it on your own, you just go to their page, download executables, and everything's there for you. You don't need to do all the work for compiling and testing everything. All right.